In this lecture, we talk about some preliminaries about complex numbers. A number z is a complex number if z can be written in the form x plus y times I, where x and y are both real numbers and where I equals the square root of -1. And so I squared is -1. Speaking of real numbers like -1, negative real numbers, just like positive real numbers, have two square roots. In the case of -1, the second square root is -I. The form x plus yi for z is often referred to as the standard form of z. X is called the real part of z and is written as re parentheses z. Variations in this notation include using square brackets or braces instead of parentheses. Y is called the imaginary part of z and is written as im parentheses z. Note that the imaginary part of z does not include I, but only the coefficient y of I. Y, or the imaginary part of z, is 0 if and only if z is a real number, because z will be equal to x, which is real. On the other hand, if the imaginary part of z were to be non-zero, then z would not be a real number, and therefore z would be imaginary. X, or the real part of z, equals 0 if and only if z equals y times I, so that z is what we call a pure imaginary number. Let z sub 1 be equal to x sub 1 plus y sub 1 times I, and let z sub 2 be equal to x sub 2 plus y sub 2 times I, with both being in standard form, so that x sub 1, x sub 2, y sub 1, and y sub 2 are all real numbers. Z sub 1 equals z sub 2 if and only if x sub 1 plus y sub 1 times I equals x sub 2 plus y sub 2 times I, if and only if x sub 1 equals x sub 2 and y sub 1 equals y sub 2. This means that the real part of z sub 1 equals the real part of z sub 2, and at the same time, the imaginary part of z sub 1 equals the imaginary part of z sub 2. We add and subtract complex numbers just as we do polynomials. We combine similar terms. Hence, to add z sub 1 to z sub 2, or x sub 1 plus y sub 1 times I to x sub 2 plus y sub 2 times I, we combine the real parts x sub 1 and x sub 2, and then the coefficients of I, y sub 1, and y sub 2. We deal with subtraction in the same fashion. We continue to treat z sub 1 and z sub 2 like polynomials to get the product z sub 1 times z sub 2, or the product of x sub 1 plus y sub 1 times I and x sub 2 plus y sub 2 times I. We FOIL the product x sub 1 plus y sub 1 times I times x sub 2 plus y sub 2 times I. F for the first terms, so we have x sub 1 times x sub 2. O for the outer terms, so we have x sub 1 times y sub 2 times I for the inner terms, we have y sub 1 times I times x sub 2, or x sub 2 times y sub 1 times I. L for the last terms, we have y sub 1 times y sub 2 times I squared. And since I squared is -1, we have minus y sub 1 times y sub 2. Writing this out in standard form, we have the real parts combined, x sub 1 times x sub 2 minus y sub 1 times y sub 2, and then the imaginary part, x sub 1 times y sub 2 plus x sub 2 times y sub 1, and then times I. Let z sub 2 be non-zero. To write the quotient z sub 1 over z sub 2, or x sub 1 plus y sub 1 times I over x sub 2 plus y sub 2 times I in standard form, we multiply the numerator and the denominator by what is called the complex conjugate of the denominator z sub 2, or the complex conjugate of x sub 2 plus y sub 2 times I. This is the same strategy that we use to rationalize a binomial denominator that contains a square root. So we multiply z sub 1 over z sub 2 by the fraction x sub 2 minus y sub 2 times I over x sub 2 minus y sub 2 times I. We FOIL the product of the numerators to get the quantity x sub 1 times x sub 2 plus y sub 1 times y sub 2 plus the quantity minus x sub 1 times y sub 2 plus x sub 2 times y sub 1 times I. We leave it as an exercise for the viewer to verify this result. The product of the denominators should be the difference of the squares x sub 2 squared and the square of the product of y sub 2 and I squared is -1, so that the square of the product of y sub 2 and I is minus the square of y sub 2. so that we get x sub 2 squared plus y sub 2 squared in the denominator. With this result, we introduce a new operation for complex numbers on top of addition, subtraction, multiplication, and division. This operation is complex conjugation. We denote the complex conjugate of z as z with a bar over z. If x and y are real, then the complex conjugate of x plus y times I is x minus y times I. And so the real part of z equals the real part of z bar. And the imaginary part of z equals minus the imaginary part of z bar. Furthermore, one can easily verify that z bar bar, or the conjugate of z bar, is z, so that complex conjugation can be called an involution or an involute operator. Going back to addition and subtraction, the conjugate of the sum of z1 and z2 turns out to be the sum of the conjugates of z1 and z2. In the product of the conjugates of z1 and z2, we put minuses in front of y1 and y2. And we find that the result is the conjugate of the product of z1 and z2. We leave it as an exercise for the viewer to check that the quotient of the conjugates of z1 and z2 is also the conjugate of their quotient. We now discuss a graphical representation of complex numbers. We often use R2 or the xy plane to graph complex numbers. We identify the point xy on the xy plane with the complex number x plus y times I, or z. When we say identify, we will make no distinction between the complex number x plus y times I and the point xy. In fact, we often refer to the point xy as the point x plus y times I, or the point z on the complex plane. As an example, the origin, or 0, 0, is identified with the complex number 0 plus 0 times I, which is equal to 0. We refer to the x-axis as the real axis, and the y-axis this time as the imaginary axis. Consider the product of z and its conjugate z bar, or the quantity x plus y times I times the quantity x minus y times I. We had already seen that this is equal to the sum of the squares of the real and imaginary parts of z, so that z times z bar is x squared plus y squared. The distance between the origin and the point z, or the point xy, is the square root of x squared plus y squared. We denote this distance as the absolute value of z. It should not puzzle the viewer that we use the term absolute value, since on the real line, the distance of x to 0 is the absolute value of x. In addition, the absolute value of x equals the square root of x squared. So we can think of the absolute value of x plus y times I, or the absolute value of z on the complex plane, as just an extension of the absolute value of real numbers on the real line with the addition of y squared inside the square root. Therefore, the absolute value of the complex number x plus y times I is indeed the distance of x plus y times I to the origin on the complex plane. We often use polar coordinates for complex numbers. Let r be the distance of the point xy to the origin. Then r squared equals x squared plus y squared. If r is indeed the distance between z and the origin, then r is also called the modulus of z. The angle theta is measured counterclockwise from the positive real axis to the radial segment of z, so that tangent theta is y over x. The angle theta is also called an argument of z and is written as arg parentheses z. X equals r times cosine theta, and y equals r times sine theta. Therefore z, or x plus y times I, equals r times cosine theta plus r times sine theta times I. And we write this as r times the quantity cosine theta plus I times sine theta. We cannot stress enough the importance of the quantity cosine theta plus I times sine theta. The quantity cosine theta plus I sine theta is actually equal to the exponential of I times theta, or e raised to the power I times theta. This is Euler's formula, which, as we can see, directly relates exponential functions to trigonometric functions. One can derive this equation using the Maclaurin series of e raised to the power t, cosine t, and sine t, where t is replaced by I times theta. We leave this as an exercise for the viewer. And so, according to Euler's formula, z, or x plus y times I, equals r times e raised to the power I times theta, or the absolute value of z times e raised to the power I times theta.